Okay, hello, this is chapter 8 of the Edexcel chemistry course, and we're now talking about acids, bases, and salts. So let's take a look at what's an acid and what's a base. You should realize the definition of acid is proton donor, base is proton acceptor. Now, what does proton mean here? When we dissolve an acid in water, it forms H plus ions, and you should realize that the hydrogen as an atom has one proton, one electron, and that's it, nothing else. So if I have H plus, that means that the one electron that was there has been lost, and so the H plus is actually something that has only a proton in the nucleus, no electrons, no neutrons. So this is what we refer to as a proton. So an acid is something that gives H plus ions, so we call it a proton donor. A base accepts this H plus ions, and it's called a proton acceptor. When a base is dissolved in water, if the base dissolves in water, it will dissolve to give hydroxide ions, which is OH minus ions. So the base that dissolves in water is called an alkali. Alkali is a base that dissolves in water. Salts are ionic substances produced from the reaction of acids and bases. So when an acid reacts with a base, what comes out of that reaction is called a salt. Now, any acid or any base can either be concentrated or dilute. If we say a solution is concentrated, whether it's acid or base, a concentrated solution has a very small amount of water added to it. That means I have a lot of solute, less water. A dilute solution is one in which you have added a lot of water to it. So this is a small amount of solute with a lot of water around it. So that's what we call a dilute solution or a dilute acid. Acids and bases can also be divided into or grouped into strong and weak. So, a strong acid is something that ionizes completely in solution. Completely in solution means it will all the atoms or all the molecules will break up to form ions. So this gives a lot of H plus ions. So the definition of a strong acid is that it ionizes completely in solution to give lots of H plus ions. You should realize that things like hydrochloric acid, sulfuric acid, nitric acid, all of these are strong acids. And what is a strong acid? It's something that dissolves in water, breaks up completely into ions, so we say it ionizes completely, so it forms a lot of H plus ions. A weak acid is something that will ionize only partially, so only some of its molecules will give H plus ions, so that means it has a solution with less H plus ions. Which ones are weak? Ethanoic acid, citric acid, which is the acid in lemon juice. These are regarded as weak acids or organic acids in general when we start to do organic chemistry. The same applies to bases, but now when they ionize, they form OH minus. So if it's a strong base, it ionizes completely to give lots of OH minus ions. If it's a weak base, it ionizes partially to give less number of OH minus ions. You should realize that things like sodium hydroxide, potassium hydroxide, normally hydroxides of any metals, are usually strong bases. A weak base that we deal with in our syllabus is ammonia. So ammonia is regarded as a weak base. Now the pHs, we will talk about pHs in a minute, but you should realize that a strong acid or a strong base ionizes completely in solution, but the acid gives lots of H plus ions, the base gives lots of OH minus ions. A weak acid or a weak base ionizes partially in solution. So if it's an acid, it gives less H plus ions. If it's a base, it gives less hydroxide ions. Now, the pH is a scale that we use to identify whether something is a strong acid, weak acid, strong base, weak base, or neutral. It is a scale from 1 to 14, or sometimes it's from 0 to 14, but let's say it's from 1 to 14. The pH, if it is small number, that is a stronger acid. If it's a big number, then it's a stronger base. So from numbers 1 to 14, the number 7, pH 7, is given to a neutral solution. So if the solution is neither acid nor base, it is neutral, we give it a pH of 7. Anything that's an acid will have lower pH than 7. Anything that's a base will have higher pH than 7. And then the strong acid will have a lower number, a lower pH than a weak acid. So things like hydrochloric acid, sulfuric acid, nitric acid, these are regarded as strong acids. So if we're told suggest the pH of these kinds of solutions, the pH can either be 1, 2, or 3. It can never be more than that. Even if we say dilute or concentrated, hydrochloric acid cannot be more than pH 3. Sulfuric acid cannot be more than pH 3. Now, a weak acid, something like vinegar or lemon or ethanoic acid or what we call citric acid, all of these are weak acids. And if we were to determine the pH of a weak acid, it is either 4 or 5 or 6. Okay, now bases, we said bases in general have pH higher than 7. So if it is just 8 or 9 or 10, we say it's a weak base. So pH of ammonia is somewhere between 8, 9, and 10. A strong base like sodium hydroxide, calcium hydroxide, magnesium oxide, any oxide or hydroxide of metal would be a strong base, pH 11 or above. So 11, 12, 13, or 14. Now, if we have solutions of acids or bases, solutions of acids or bases are all colorless. So just looking at the solution of an acid or a base, you cannot identify if this is an acid or a base. So we use something to help us to determine if the solution that I have in the beaker, for example, is an acid or a base. So the substance that we use is called an indicator. An indicator is a substance that has different colors in acids and bases. So if I give you anything and you put it in acid, it has a color, in base it has a different color, then that is an example of an indicator. The indicators that we use in the lab normally are either litmus paper, universal indicator paper, phenolphthalein, or methyl orange. So let us talk about this. Litmus paper. Litmus paper is used just to determine if something is acid or base. It doesn't tell you if it's a strong acid or a weak acid, strong base or a weak base, pH 1, pH 14, it doesn't tell you. It just says whether it's an acid or base. This is because we just have two colors of litmus paper. Litmus paper is either blue or red. If I put the blue litmus into a solution and it turns red, that means I have an acid. So that solution in the beaker on the left is an acid. If I have the red and I put it into a solution and it becomes blue, then that is a base. So the base causes the litmus paper to become blue. The acid causes the litmus paper to become red. Now, the other kind of indicator that we can use is universal indicator paper. And as we said, the litmus paper just tells me if something is an acid or a base, but doesn't tell me what is the pH. Now, if I want to determine the pH of a solution, so if he says, how do we determine the pH of a solution? We say, insert a universal indicator paper, compare the color to the chart, because this paper is, originally, it's just a yellow paper. It looks like the litmus paper, but it's a yellow paper. And if you put it into different solutions, it turns into different colors. And then we have a chart next to the paper that tells me if it is very red, then it's pH 1. If it is this color, it's pH. So you're not required to memorize all of these colors, but you need to know that on the edges of this pH scale, it is very similar to the litmus. For example, the pHs 1 or 2 are red. This is a strong acid, just like the litmus. pH 13, 14 are blue, just like the litmus. So, very strong acid, very strong base, it's just the same color as the litmus. It's either red or blue. Neutral by pH 7, if something is neutral, the universal indicator paper will turn green. So if I put universal indicator paper into water, for example, it will turn green. If I put it into a strong acid, sulfuric acid, it turns red. If I put it into a strong base like sodium hydroxide, it turns blue or different shades of blue. The only other color that you need to know is the color of weak acids. What happens if I put universal indicator paper into weak acid? Can you see what colors you have? It will either give you yellow or orange. So when we're trying to determine the pH of something, we say insert universal indicator paper, compare the color to the chart. You are required to know that if I put it in sulfuric acid, it is red. If I put it in sodium hydroxide, it's blue. If I put it into something neutral like water or sodium chloride, it will be green. If I put it in something that's a weak acid, it will be orange or yellow. You're not required to know the other different shades of blue that you have in there. Okay, the other indicators, so litmus paper and universal indicator paper, these are papers. Sometimes they can be solutions also. You can have a solution of litmus or a solution of universal indicator paper. But the solutions we usually use in the lab are phenolphthalein or methyl orange. We'll be talking about something called titration, and these are the kinds of indicators that we use in titration. And you have to remember the colors in acid, base, neutral for each of these. So phenolphthalein, if I put it in a base like what? Like sodium hydroxide, you realize that any base would either end with oxide or hydroxide, and an acid will always start with an H. So anything that starts with an H, we said before, is an acid. Okay, if I put phenolphthalein solution, and this is usually a solution, we usually put 3 drops of phenolphthalein into the solution. If I put it into a base like sodium hydroxide, it turns pink. If I put it in acid or neutral, it's colorless. Okay, you have to remember these colors. Now, methyl orange. Methyl orange in acid, it's similar to the base. So the phenolphthalein, is similar to the base of the phenolphthalein. So the phenolphthalein is pink in base. Methyl orange is red in acid. Okay. The neutral, it is called methyl orange. That is because it is orange in the neutral. If I put methyl orange into a base, it turns yellow. Can you remember these colors? So methyl orange, in a base it's yellow. Phenolphthalein, in a base it's pink. Methyl orange, neutral is orange. Phenolphthalein, neutral is colorless. Methyl orange in an acid, it's red. The phenolphthalein in an acid is colorless. So you have to remember that. Okay, reactions of acids and bases. The most important reaction is neutralization reaction. A neutralization reaction is the reaction between acid and base. When I react an acid with a base, what comes out is called a salt. Now, something like HCl, for example, hydrochloric acid, we said if I say suggest the pH of hydrochloric acid is a strong acid, so it has a pH of 2, for example. 1, 2, or 3 will be fine. Sodium hydroxide is a strong base, so it will have pH around 12. Now, when I add them together, they form salt, which is sodium chloride, and water, and both salt and water are neutral. So their pH is 7, and that means that I took an acid with a base and I reacted it together, and what came out is neutral. So this is called a neutralization reaction. Okay, acid plus metal. If I react an acid with a metal, it gives a salt plus hydrogen gas. Are you paying attention to these things? So acid and base gives what? Salt and water. Acid and metal gives what? Salt and hydrogen. So if I have zinc plus HCl, so zinc plus hydrochloric acid will give zinc chloride. So zinc chloride is a salt plus hydrogen gas. Okay. Now, the other reaction is acid with carbonate. Any carbonate reacts with acid. When a carbonate, something carbonate, reacts with acid, it will give a salt plus carbon dioxide plus water. Now, which salt or what exactly comes out depends on which acid are we talking about and which carbonate are we talking about. So, for example, if I have hydrochloric acid with calcium carbonate, now it gives calcium chloride plus carbon dioxide plus water. Can you see that? Okay. The other type of reaction is a base with a salt, ammonium salt. Now, a base with ammonium salt gives ammonia gas. And we will be talking about that when we talk about tests for ammonium. If you add a base like sodium hydroxide to something that has ammonium, like ammonium sulfate, for example, that will give me a salt, sodium sulfate, water, and ammonia gas. Okay, so always remember that in order to get ammonia gas, we need to add a base to an ammonium salt. Ammonia plus acid gives ammonium salts. So ammonia is a base, but is the only base that we deal with that doesn't have oxide or hydroxide. Remember I told you that bases end with oxides and hydroxide? Actually, ammonia is an exception. So ammonia is something that doesn't have oxide or hydroxide. So the base, when it reacts with acid, it gives only salt, not salt and water like the other bases. So for example, ammonia plus hydrochloric acid will give ammonium chloride. Ammonia plus nitric acid will give ammonium nitrate. Ammonia with sulfuric acid will give ammonium sulfate, and so on. Ammonia with phosphoric acid will give ammonium phosphate. Okay, now HCl, we've talked about HCl before, but let's go over this again. HCl is a unique compound. As a gas, it is covalent, and we've drawn the dot and cross of HCl as a covalent compound because we said hydrogen is a nonmetal, chlorine is a nonmetal, so when they react together, they form a covalent compound, and we wrote the dot and cross in which they share a pair of electrons. But then, as a gas, when I take this gas and dissolve it in water, it actually ionizes to form H plus and Cl minus. Anything that gives H plus ions in water is an acid. So HCl, which is hydrogen chloride as a gas, dissolve it in water, it ionizes to form an acid, hydrochloric acid. When you dissolve it in any other organic solvent, anything, methyl benzene, for example, or any organic solvent, it doesn't ionize, so no acid is formed. And that means that when you dissolve hydrochloric HCl in water, it behaves as a normal acid and it does all the reactions that we just talked about with acids. But when you dissolve it in organic solvent, it doesn't ionize, so it is not an acid at all, and it will not do any of the reactions that the acids do. Okay? Now, next we said, I was saying also that oxides of a metal or hydroxides of a metal are usually basic. Actually, there are exceptions. So, oxides of a metal or oxides of a non-metal can either be acidic or basic or amphoteric or neutral. These are the different types of oxides that we can have. Now, if the oxide is an oxide of a non-metal, carbon dioxide, nitrogen dioxide, sulfur dioxide, sulfur trioxide, silicon dioxide, all of these are oxides of non-metals. Now, all of these are acidic oxides. And the fact that they're acidic means they will react with base. Remember that we said a neutralization reaction is acid plus base to give salt plus water. So if I say that anything is an acid, that means that it will react with a base. If I say that anything is a base, that means it will react with an acid. So oxides of non-metals are acidic, and that means you can react any of these with a base. Now, oxides of most of the metals are basic. So calcium oxide, copper oxide, magnesium oxide, sodium oxide, these are basic. Basic means they will react with acids. But then there are exceptions. So if we say that oxides of most metals are basic, actually some of them are what we call amphoteric. Now, the word amphoteric oxide means a substance that can act both as acid and as a base. So amphoteric, I just said that if it's acid, it should react with base. If it's base, it should react with acid. But usually an acid will not react with acid. A base will not react with a base. But if something is amphoteric, it can act as both. So an amphoteric oxide like zinc oxide or aluminum oxide or lead oxide. These are the amphoteric oxides that we're studying. If you react it with an acid, it will react. So it acts as a base. If you react it with a base, it will react. So it's now acting as an acid. So it can act both as acid and as base, so they are amphoteric oxides. Now, we said oxides of nonmetals at the beginning. Oxides of nonmetals are what? Are acidic, but there are exceptions. Some oxides of some nonmetals are neutral. Now, if something is neutral, that means it doesn't react with acid, it doesn't react with base. Do we understand this? So if something is acidic, it reacts only with base. If something is basic, it reacts only with acidic. If something is amphoteric, it will react with both acid and base. If something is neutral, it will not react with any of them, acid or base. And you have to remember which one is acidic, which one is basic, which one is amphoteric, which one is neutral. Could you do that? Okay. So, magnesium oxide, remind me again, we said magnesium oxide is a base. If you put it in water, it gives magnesium hydroxide, so that's a base. But carbon dioxide, we said, is acidic. So if you dissolve it in water, it forms an acid. It forms what we call carbonic acid. SO2, sulfur dioxide, is an oxide of a nonmetal, but this is acidic. You should remember that SO2 is acidic. This is because when you dissolve it in water, it forms an acid called sulfurous acid. Now, SO3 is also acidic. When you dissolve it in water, this is what forms sulfuric acid. Okay? Okay, how do we prepare salts? So we said a salt is a substance formed from reaction of acid with base. Now, the method that we use in the lab to prepare the salt depends on which salt are you trying to prepare and what substances you're trying to prepare it from. And in order to determine which method to use, you need to remember what is soluble and what is not soluble. What is something that dissolves in water and what is something that does not dissolve in water. You have to remember, all nitrates are soluble in water. So anything nitrate is soluble. In any equation, if he gives you or if he asks you for a state symbol, if it is something nitrate, it is probably aqueous. Sodium, potassium, ammonium salts are all soluble. So sodium anything, potassium anything, ammonium anything, all of these are soluble. So their state symbol is AQ. They all form aqueous solutions. All acids are soluble. Things like barium chloride, copper sulfate are things that we use a lot in this syllabus, and you should know that these are things that dissolve in water. Now, the things that do not dissolve in water, or they will form what we call a precipitate, so if they're formed in reaction, they come out as a solid. Things like barium carbonate, calcium carbonate, actually all carbonates except if it is sodium carbonate, potassium carbonate, ammonium carbonate. Remember that we said sodium, potassium, ammonium salts are all soluble. Other carbonates will not dissolve in water. So something like barium carbonate, calcium carbonate, these are not soluble. And then silver halide, silver chloride, silver bromide, silver iodide, these are not soluble. They are precipitates. They are solids. Lead chloride, lead bromide, lead iodide, all of these are precipitates or solids. Barium sulfate is a white solid. Copper oxide is a black solid. All metals, of course, do not dissolve in water. So, to prepare a salt, I have one of three methods to choose from. I can either use a method called titration, or a method called neutralization, or another method called precipitation. These are the names of the methods. Now, when do we use each method? Titration, you will choose if you're trying to make something soluble from something soluble. You're trying to make, for example, sodium chloride from sodium hydroxide. We said sodium anything is soluble. So everything is soluble, then I use titration. If I'm trying to prepare something soluble, but I'm starting with an insoluble reactant. So I'm starting with a solid that doesn't dissolve and I want to make something that's soluble. Then I will do the method that we're going to talk about, which we call neutralization. Precipitation is the method that you choose if you're trying to prepare something that is in solid. So let's talk about each method in detail. Titration, first of all, we said you choose this method if everything you have is soluble. So you're trying to prepare something that is soluble and you're starting with things that are soluble. So I'm trying to prepare, for example, sodium chloride. I want to make crystals of sodium chloride. first of all, which acid and which base should I use? If I'm trying to make sodium chloride, then the base has to be sodium hydroxide and the acid has to be hydrochloric acid. Okay, now that means that in order to make sodium chloride, all I need to do is just add sodium hydroxide to HCl, and I will end up with sodium chloride in water, and that's a sodium chloride solution. Good. But I have a simple problem. How much acid should I add to the base so that I don't add too much acid and I don't want to add too much base? Because if I add up too much acid, then I will have my salt plus the extra acid that I added. If I add too much base, then I'll have my salt plus the extra base that is added. I will not be able to separate them from each other. So titration is a method to determine how much I should add exactly in order to have a neutral solution, sodium chloride in water, no excess, no extra base, no extra acid. So what we do is we use a burette and a flask. And the first thing that we want to do is we want to put a specific amount of the base in the flask. So we put that using a pipette. You remember which one is a pipette? The pipette was the apparatus that had no tap. It just has a mark, and if I fill it to that mark, it has exactly 25 centimeter cubed. So I'm going to put exactly 25 centimeter cubed of sodium hydroxide solution into a flask using a pipette. And I'm going to fill the burette with the acid. You can also do it the other way around. You can put the base in the burette and the flask contains the acid, but let's do it this way. So now we have the sodium hydroxide in the flask and we have the burette containing the acid, and I have another tiny little problem. All of this are colorless solutions. How do I know if I've added enough acid to neutralize the base? I need to add an indicator. So in the flask, I now have 25 centimeter cubed of sodium hydroxide solution. I add to it 3 drops of phenolphthalein. Do you remember the color? You should remember that when I add phenolphthalein to sodium hydroxide is a base, phenolphthalein is pink in base. So the solution turns pink. Then I start to add, of course, I'm going to fill the burette with acid, and I'm going to note the initial reading of the burette. And then I'm going to start adding dilute HCl from the burette to the flask until I add a drop and the pink color disappears. So we're adding drop by drop until the pink color just turns colorless. And I note the final reading of the burette and determine how much acid I have added. Now I know that if I have 25 centimeter cubed of sodium hydroxide, I should add this amount of HCl that I determined from the burette. So now I can repeat the experiment. Why do I need to repeat the experiment? Why not just take this flask and work with it? This flask contains indicator. I don't want indicator with my solution. So I'm going to repeat it. That means I'm going to bring a brand new flask, clean flask, put 25 centimeter cubed of sodium hydroxide and the required amount of HCl that I determined from the burette into the flask without using indicator. Then I take this solution, which now has sodium chloride and water, and I want to make crystals out of it. Do you remember how to do crystallization? We heat the solution to point of crystallization, cool, filter the crystals, wash with a few drops of distilled water, and dry between filter papers, and this will give me pure, dry crystals of sodium chloride. Do we understand that? Okay, so this is the pink color that you expect, and once you put a drop that is enough to neutralize, the pink color immediately disappears. Okay, let's try this question. This apparatus can be used to find the volume of dilute sulfuric acid needed to neutralize 25 centimeter cubed of aqueous sodium hydroxide. So he's doing a titration here. Describe how to use the apparatus to find the volume of dilute sulfuric acid needed to neutralize sodium hydroxide. So basically he's telling you, describe in detail how to do titration. Do you remember how to do titration? So we said put 25.0 centimeter cubed of sodium hydroxide into a flask using a pipette. Now he has in his diagram methyl orange, so we're going to use methyl orange. Add 3 drops of methyl orange to the flask. Then we fill a burette with the acid, dilute sulfuric acid. He specified that we're going to use dilute sulfuric acid. Note the initial reading of the burette. So here we're explaining in detail exactly how we do the titration. I fill it with the acid, I note the initial reading of the burette, and then I start adding acid from the burette until what? Remember that this is methyl orange. When I add it to base, it is initially yellow. I keep adding the acid from the burette until the yellow solution becomes orange. We said the neutral solution, in neutral solution, the methyl orange is orange. Note the final reading of the burette. So I read the final reading from the burette. I subtract the final minus the initial reading to obtain the volume of acid used. And then I can repeat this experiment. This titration needs to be done more than once. It is usually done 3 or maybe 4 times in order to obtain what we call concordant results. So let's say the first time I got a specific volume. I found that I need whatever, 30 centimeter cube of the acid. I need to repeat it again to make sure that I get the same result, so that I can have results that are within about 0.2 of each other. This is called concordant results. So let's say a student makes an alkali solution by dissolving a small volume of cleaning liquid in deionized water. Deionized water means distilled water. Or pure water. He then titrates a sample of this solution with an acid until neutralization is complete, and he gives you the diagram of the burette. So you're supposed to read the diagram of the burette. Remember that we read the top of the burette from the bottom of the meniscus. Do you understand the meaning of meniscus? Meniscus is the top of the liquid is sort of slanting upwards on the sides. You look at where it is at the bottom. So for example, can you read the burette reading before adding the acid? What is the burette reading up there? And notice that a burette is going from up to down. So burette reading in before is 3 point something. Can you see that it's 3 point something, not 4 point something? It's 3 point something. So this is actually 3.15. Now after, what is the reading after? It's 20 point something. So after it's 20.8. And he says use the readings to complete it, given all values to the nearest 0.05. If he says to the nearest 0.05, that means that he wants it in 2 decimal places. So your answer must be in 2 decimal places. The volume of acid added is just the before, the after minus the before, or the final minus the initial. So this means that this experiment used 17.65 centimeter cubed of the acid. Okay, now another student does a titration using a solution of a different cleaning liquid. The table shows her results. So here he has already calculated for you the volume of acid added. In one case was 26.25, 25.10, 25.75, and so on. And he's telling me that concordant results are those that differ by 0.2. So I want to choose out of this 5 trials, I want to choose the results that are within 0.2 of each other. So the difference between them cannot be more than 0.2. And he's saying place ticks in the table to show which results are concordant. So look at the results of the volume of acid, 26 point something, 25 point something, 25 point something, and so on. Which of these are within 0.2 of each other? Can you see which one? So this is 25.1, 25.3, the difference between them is 0.2, and 25.2, that's the difference is less than 0.1 from the others. So these 3 are called concordant results. And when we're trying to get the average, we use only the concordant results. We ignore the others. So the average of these 3 is just its addition divided by its number. So you add them all up, divide by 3, then your answer is 25.2. Do we understand that? Okay. In another experiment, the student is provided with a solution of sodium hydroxide and a solution of 0.02 mole per decimeter cube phosphoric acid. She does a titration to find the volume of phosphoric acid that reacts with 25 centimeter cubed of sodium hydroxide. So in this case, she has 25 centimeter cubed of sodium hydroxide in the flask, and she has phosphoric acid in the burette. And he explains the method, and the first question is, name a piece of apparatus that will give a more precise measurement of the volume of sodium hydroxide. So I go back. What did she use to make the volume of sodium hydroxide? She used a measuring cylinder to add 25.0 centimeter cubed of sodium hydroxide. Of course, we said we cannot use measuring cylinder to add 25.0. We need to use, what we usually use is a pipette. Add a few drops of phenolphthalein indicator to the flask. Okay, the next question says, suggest why the student places the flask on a white tile. Why do you think the flask is on something white? Okay, of course the flask is on something white in order to see the color change clearly. We're obviously trying to add acid from the burette until there is a color change. So if the flask is on something white, then we can see the color change clearly. Give the color change of the phenolphthalein indicator. So he added phenolphthalein indicator. Let's go back. He added phenolphthalein indicator to sodium hydroxide in the flask. When you add phenolphthalein to sodium hydroxide, it is pink, and then when it is neutral, it becomes colorless. You have to know these colors. The student dries the flask after washing it with distilled water. Suggest why it's not necessary to dry the flask before repeating the titration. Remember that when we do titration, we're trying to react a certain amount of acid with a certain amount of base. So if I put that amount of base, specific amount of base, even if it's in a lot of water, that doesn't change the specific amount of base that is present in the flask. So water does not change the number of moles or the amount in the flask. The diagram shows the student's burette readings for her titration before, so we need to read these burette readings. Can you read the one before? Which one is the one before? Okay, remember we said this is a burette, so you're reading it from up to down. In any case, you're always reading it from the small number to the big number. Okay, so this is 1 point something. Can you see it's 1 point what? It's 1.45. So that means the after minus the before, that comes out to be 21.35. Okay, another student does the experiment 4 times and she has these results. Place ticks in the table to show which results are concordant. Which of these are concordant? 21.5, 21.35, 21.4. All of these are within less than 0.2 of each other. So when I want to calculate the average, I use all of them divided by 3. So the average volume of acid needed is 21.42. Okay, this is an example of an investigation that he might ask you to explain. So it says oven cleaners contain an aqueous solution of sodium hydroxide. Plan an investigation to show which of the 2 different oven cleaners contains the more concentrated solution of sodium hydroxide. You are provided with common laboratory apparatus and chemicals. So he's saying I have solutions of sodium hydroxide. I have 2 different solutions of sodium hydroxide. And I want to know which one is more concentrated. You should realize that we're going to use titration. And basically what we do is we put the solutions into the flasks. We do the titration with a specific acid. The one that uses more acid is the one that is more concentrated. So we say put 25 centimeter cubed of the first sodium hydroxide solution to a flask using a pipette. Add 3 drops phenolphthalein. When you add the phenolphthalein to sodium hydroxide, the solution turns pink. Add dilute HCl from burette until the pink color disappears. Note the volume of acid used, and then I repeat it with the same amount of the other alkali solution, and I determine which one uses more acid. The one that uses more acid is more concentrated. Do you understand that? Okay. Another method of preparing salts is neutralization. So this is the name of the method, not a reaction. Neutralization is a method in which I start with something insoluble. So I'm starting with a solid, like copper oxide. Copper oxide, you should realize as we go along that copper oxide is a black solid that doesn't dissolve in water. So I'm starting with something insoluble, and what I'm trying to prepare is a soluble salt. So I'm trying to prepare, for example, copper sulfate. Now, copper sulfate is a soluble salt. It's a blue salt that dissolves in water. And I want to start from copper oxide, which is a solid. So I cannot do titration. You can't do titration if you're starting with something a solid. So you need to do a different method. So the method that we use now is called neutralization. And what we do is we put some of the solid copper oxide into a beaker containing sulfuric acid, and when we take a solid from the container and add it to the beaker, I use a spatula. So we add the solid copper oxide using a spatula to 25 centimeter cube sulfuric acid in a beaker, and when I add it, it will dissolve and react. And then I add some more, it dissolves and reacts. And then I add some more and dissolves and reacts. Until what? Until all the sulfuric acid has reacted. Now, if all the sulfuric acid has reacted, then if I add any more copper oxide, it will not react and dissolve. It will stay in the beaker. So I keep adding and stirring and adding and stirring until excess solid remains in the beaker, right? And then I take this, and I don't want this excess solid back, it's just extra copper oxide that I don't want. So I go ahead and do filtration. I filter this mixture through filter paper and funnel. What remains in the filter paper is the extra copper oxide that I added, so I don't want that. That's the unreacted copper oxide, I don't need that. And what I want is the solution that goes down. The solution that goes down is the copper sulfate solution that I want. Now I want to make crystals, so I take that solution from the flask, heat to point of crystallization, cool, filter the crystals. I can then go on and say dry between filter papers if I need it to be dry. Do we understand what we did? Now, the last method of preparing the salt is called precipitation, and we use that if I'm trying to make something that's insoluble. So if I try to prepare silver chloride, and silver chloride is something that doesn't dissolve in water. Now that means that I need to start with two things that are soluble. So I need silver, something that is soluble. Remember that we said all nitrates are soluble. So silver nitrate is a soluble salt. And I need something chloride, which is soluble. So I can use sodium chloride because we said sodium anything is soluble. In this case, if I just add the silver nitrate solution to the sodium chloride solution in a beaker or in a flask, I get a white precipitate of silver chloride. So this white solid that forms at the bottom of the flask is the silver chloride that I want. Now, how can I separate it? I can go ahead and do filtration. The precipitate or the silver chloride solid that I want will remain as residue in the filter paper, and I can wash that with a few drops of distilled water dry between filter papers. Are we okay with all of this? So, please study this chapter, it's important. Go over it and try the questions as much as you can, and we'll discuss its answers in the next lesson.